Hi, good afternoon, everyone. Welcome to our fifth episode of our Gov at Cloud webinar series, Gov at Cloud, processing real world event streams. My name is Victoria. I'm one of the customer success manager in Topan Aquara. I will be your host today. Thank you for taking time out to be with us today. Before we begin, for the benefit of the new attendees, let me share with you how the Gov at Cloud series came about. During the recent years, technologies have been evolving from cloud computing to artificial intelligence. Many organizations, including the public sectors, are always seeking out to leverage on the innovations to improve their business operations. As a company focusing on digital government transformation, Open Aquaria has helped various government agencies transform their organization operations from migrating their systems onto the cloud to implementing data-driven solutions using machine learning and AI techniques. Along the way, we pick up some learning points that we thought could be beneficial for the industry. So here we are putting together a series of Gov at Cloud webinars to share ideas, and hopefully it will be beneficial to you. In the first two episodes, we focus on topics related to government compliance solutions on the public cloud. In the first episode, we spoke about how content inspection should be the important feature of API gateways designed for government systems. The session also touched on integrating with identity service providers using SAML 2.0 and our new OIDC relying party feature. The second episode was on the DevSecOps and its different stages for governments on the public cloud. In our third episode, it was a feature about text analytics and computer vision, essentially how AI and machine learning can be applied. Our previous episode, which is the fourth one, we shared on the importance of having event-driven microservices, and today is part two of the event-driven series focusing on streams processing. Okay, let us do a time check first. The time now is 1:03. Seems like most of the attendees are in. Let's kickstart the webinar. My name is Victoria. Together with me are Anson and Yen Hock. They are our presenters today. Let me do a quick introduction for the both of them. Anson is our first presenter.
Hi, everyone.
He's one of our experienced digital government transformation architects. He has been in the trenches architecting various systems for government. He works closely also with our CTO and other fellow architects on applying the right microservices strategy for digital government. He has a passion for applying new architects to leverage on the new technologies. Yen Ho is our second presenter.
Good afternoon, everyone.
He will be touching on the demonstration of today's topic. He's one of our senior consultants from the digital government transformation team. He has been proposing solutions to the different government tenders and is very experienced in system implementation, from requirement gathering to system deployment and support. He is also certified as Scrum Master in implementing agile projects and has conducted several discovery workshops for our customers and prospects in supporting the utility of their systems. Looks like we have good speakers today as well. I believe all of us are excited for the webinar to begin. But before the webinar begins, let's just do a little housekeeping to run through. This is a live webinar. We will be recording the session, which will be releasing onto our YouTube channel. So after this session, do heads up over to our YouTube channel and make sure you subscribe to our channel and give us a big thumbs up. If you have questions during the presentation, do also put them into the QA box right below the screen of the webinars at the below button. There's a tab Q&A. You can text there for any questions. And also, lastly, if you'd like to invite us to present to your team or have questions after this session, do also drop us a note, an email at info@topanaquera.com. Okay, without further ado, I will hand over the time to Anson, who will be sharing with us on the topic of streams processing. Over to you, Anson.
All right, thank you, Victoria, and a very good afternoon to everyone. Welcome to our Gulf at Cloud webinar, and thank you for being here with us today. So let me briefly introduce myself. My name is Anson, and I'm delighted to be here today to talk to you about stream processing. Today's topic consists of two parts. So in the first part, I'll be covering the concept of stream processing and how we can leverage it to empower people, organizations to an increased access to data. Next, I'll pass the presentations to Ian Hock, who will walk through with you an example of how we can leverage stream processing to tap on real-time events to build a more anticipatory systems to better serve citizens' needs. This will then be followed by a Q&A session. But please feel free to drop your questions in the Q&A windows anytime so that we can pick them up later. So before we get into today's topic, we'll be starting a poll. So kindly help us to answer the poll questions. This poll questions is to help us better understand which analytic tools are your organizations currently using. Right? So whether are you using a more traditional data warehousing systems or more modern big data processing such as Hadoop, or even probably you may have already embarked on stream processing, or you probably may not have any of the above, right? All right, thank you for submitting the poll. We can see that most people are still using traditional data warehousing systems to process data, right? So that brings us to today's topic. So in today's digital age, with the explosions of the real-time data, for example, you have social data, you have IoT, data from IoT devices, right? You have data from mobile phones, you have locations data from your mobile phones. Is the way that we process data still relevant? Sorry, a minute. To answer these questions, let's take a look at how traditional data warehousing, even more modern big data processing, like Hadoop processes data. Right? Traditional data warehousing or even more modern big data employ batch processing strategy, which is to process the data at rest. In batch processing, an event gets stored in the database after it happens. Right? Periodically, this data will be extracted from database. So for example, maybe every 15 or 30 minutes, then you will go through some ETL process, right? Extract, transform, load, and the data processing, and eventually results in the data that can be consumed by the consumers, such as for business intelligence, for search and explore, or used by other enterprise applications. The problem of this strategy is that it's high latency from the point the event happens to the point the data can be used. When you get the files from the source or you get the data from the database, it's already old. When you load it into the ETL, it gets older. When you process the extracted data, it gets even older. Right? So you don't really have an up-to-date data. And then we have streams. Streams are sources of data, for example, that you may get from mobile apps, IoT devices, right? Or even things like location or end users. So typically, these are data that are smaller in size, but higher in volumes. So for example, if the device sends its users' locations every seconds, and you have 1,000 users accessing your systems, you basically get 1,000 records per second. So can we use back the same data processing pipeline to process the data? Sure, you can. But the problem that you're going to face is the high latencies. Imagine if the stream of data is regarding your users' live locations. Your users will be streaming in their live locations every single second. However, due to the latency of batch processing, you only process and get hold of your users' live locations 15 or 30 minutes later. By then, your users may have already moved on to another locations. This is a good use case where you will need access to the data within minutes, seconds, or even milliseconds, right? As if you're not getting up-to-date data, it's going to give your system wrong information and may end up creating frustrations to the end users rather than creating a value-adding services. So to summarize the issues with batch processing, basically you have data where we persisted in some database, and after we persist it, we have another analytics components that we run and get some results. The problem of these two components are they are actually separate components, and as such, how would the analytic components know when there's a new data? So typically, it will be through periodic polls to poll data regularly. For example, every 15 minutes, every 30 minutes, or even in hours in certain cases. So as I shared earlier in my slides, from the time that the data happens or the events happens till the time that the data is processed, analyzed, and can be used for meaningful operations or intelligence, the data is already out of date or irrelevant. So we are really reacting to the data rather than proactively acting on the data. Stream processing, on the other hand, instead of persisting the data, we directly do some analytics on it. You get millions of events streamed into your systems, right? However, you may not necessarily react to every single event. Right? Usually in the stream processing, you get a lot of events and you may have different use cases on what you want to find depending on your business needs. For example, you may want to do fraud detections. Right? So what you want to do is really to find anomalies. However, not every event is an anomaly. So probably one out of every thousands or every millions of the events is an anomaly. So during the analysis of the data itself, we already filter out the normal data and only focus on the anomalies. And for those anomalies found, we can then decide to do something about it. For example, we may want to store the events for audit purposes, but most importantly, you want to act out immediately. Right? So for example, if we are talking about grant application system, we may design the system to immediately block the applications or block the disbursement of the fund. So with stream processing, it gives you these capabilities to actually introduce immediate actions on the anomalies itself, as it is processing the events as it occurs or processing data in motions. Right? One good real-world example to illustrate the difference between batch processing and stream processing is a taxi company price surcharge model. How traditional taxi companies determine the price surcharge is by looking at historical data to understand service usage trend. So for example, in the morning during the 6 a.m. to 9:30 a.m., right, you may have high usage based on the past few years' data. Hence, the company set out strategic decisions to introduce peak surcharge during the time period, whether it is really truly peak or not. And for midnight charge, okay, typically the problem of midnight, the like 12 a.m. to the 6 a.m. in the morning, typically you have lesser drivers on the road, right? So they have introduced this as a way to actually drive the drivers to actually provide the supplies of the taxi itself. And then same goes for the locations, all right? So it's also by analyzing the data over a period of time to understand that, okay, so only certain locations you actually have more demand. That's why they introduced the surcharge. However, one thing that was not taken into considerations is that the data is aggregated across time. You may not have the same number of demand every single day or every single hours. Ride-hailing company, right, such as Grab, on the other hand, instead of depending on historical data, is based on real-time data to determine its price. So basically, the price is based on real-time demand, right? So for example, the price you book at different timings are different. And the price that you book at the same timing but different days may also be different. This is because the price differs from day to day and time to time. And it is impossible to implement using traditional data processing models that's based on processing aggregated data. Because you're processing and aggregated data across a different time, a long period of time, should I say. Another benefits of Grab has from utilizing the real-time data is that it's able to perform effective resource allocation. By doing real-time analysis of its users' location, Grab is able to determine locations where demand is higher and channel the supply of drivers to the location more effectively. As opposed to what I've shown earlier on, where you're actually using midnight surcharge to drive the supply of the drivers itself. So you may ask, how do Grab search pricing, such strategies benefits the government sectors as a non-profit organizations? We'll use some use case for public sectors to illustrate the benefits of implementing stream processing to process data in real time. One of such use case where stream processing will be coming as relevant is the real-time emergency care systems. Currently, the ambulance service in Singapore will send its patients to its nearest hospital that has the necessary equipment. So stream processing in this case may be able to further enhance the process by analyzing some additional real-time attributes, right? Such as the real-time emergency bed occupancies of the individual hospital, real-time traffic conditions of the roads. Right? So as illustrated, based on the nearest distance, the ambulance should send the patient to hospital B. Right? However, due to the traffic conditions towards hospital B, sometimes, the traffic conditions may be really, really bad, right? Which will cause the ambulance to much delay. So in these scenarios, with the real-time traffic data, the ambulance can be better informed and look for alternate hospitals. Right? And based on that, actually, the next nearest distance could be hospital A. However, if we also pull in information such as your emergency beds occupancy, we may be informed to say that, okay, hospital A could be overloaded, and as such, it may cause its patient to be unable to receive immediate attention. It may very well end up that hospital C, though being the furthest away from the two hospitals, may be the best options for the patients to seek immediate medical care. Another use case that we thinks that where the stream processing may come in relevance is what we call as a smart traffic control systems. Have you been caught in a situations where you see that there are no vehicle on the adjacent traffic light, but your traffic light of your directions keep turning to red and causes traffic to build up in your directions? We think that it can be further reduced if there are some smart detection system that can detect the presence of vehicles at traffic light junctions and uses logics and algorithms to analyze real-time traffic data to better manage the traffic light timing to allow for better and smoother traffic. Right. So before I pass the presentation here, I'll summarize some of the differences between the batch processing and stream processing. So in terms of the input, the batch processing models, the source data are usually from the static files or data that are persisted in the database, while the source data for stream processing are usually from event streams. Batch processing processes a snapshot of data and only responds after the events has happened, which, as I earlier mentioned, it causes high latency. While stream processing continuously processes the data as the events occurs. So this allows businesses to tap on and process data faster. Okay, so we'll go into the next sections, which is the demo. But before I pass the presentations to Yan Hock, so you see that there are some questions being posted. So maybe just let me quickly pick up one of the questions. Right. You mentioned that the main issues of batch processing is high latency due to it being polled periodically. So if I reduce polling period to every 30 seconds or even 1 minute, I can also achieve the real-time effect, isn't it? Okay, practically, you will not be able to set the polling period too short. Right? For example, so if you set the polling period to every second, your machine will just keep on doing polling and nothing else. And in addition, you also need to consider how long it takes for a batch shot to complete its processing. So if your batch shot requires 10 minutes to complete its processing, that's how fast you can get. You can't set any lower than 10 minutes. And if you do things like big data, you will know that it does not make sense to run the batch shot even for every 30 seconds. Because just by starting the job itself will take 30 seconds and you have not done any work yet. So typically, polling in traditional batch processing system might be in a span of 30 minutes or an hour. Right? That's why the difference of the batch processing versus the stream processing. Okay, we'll leave the questions to after the demo. So with this, I'll pass the presentations to Yan Hock, who will walk us through an example of how we can leverage on stream processing to tap on real-time events. Right, over to you, Yan Hock.
Thank you, Anson. Thank you, Victoria, for the great introduction earlier. So it's great to be here speaking to all of you today. I'm Yan Hock, and I'll be showing you a short demonstration on stream processing. There are many use cases where stream processing is useful. Some of them has been already shared by Anson earlier. However, the flash flood that just occurred 2 weeks ago on November 2nd, she created an opportunity for us to showcase the power of stream processing. Were you caught out there in that flood? What if we can warn you? So using stream processing, okay, we can in real time process and analyze data such that we can provide flood warning to you. So let's explore this further. Before I proceed to the demo, I would like to say that we are no expert in predicting flood. What you see today here is purely imaginative. It is just to illustrate the power of stream processing. So one of the most convenient ways to receive flood warning is through a mobile application. So similarly, in this short demo, we have created a simple mobile application to receive flood warnings. So what you see here on the left, is a simple flood warning mobile application. Okay, I'm currently located in my office in Toa Payoh. So automatically, the mobile application is able to send my current location to the service. As the weather today is very sunny, there is no flood warning. So I'm going to leave this mobile app here running on the left. In order to provide flood warning, we need to have weather station data. Okay, we need to know whether what is the weather now, whether is it raining. We probably will also need to know what is the forecast, whether will it be raining in the next 20 minutes, 30 minutes. But more importantly, we need the weather station data in real time. I mean, what good is a mobile app if it can only tell you there's a potential flood 30 minutes ago? You may be already stuck in that flood. So in today's demonstration, we will not be consuming data from the over 60 weather stations across Singapore. Instead, we have created a simple weather station simulator. And this weather simulation will be sending real-time data. Okay, so let me pull out the weather station simulator. So as you can see here on the right, it's a simple simulator that allows me to indicate 3 values. The first is the location. So this is to mimic where the weather station is located at, be it in Ang Mo Kio, Bishan, Bukit Batok, and so on. The second value that we can indicate is the current rainfall. So in patches of millimeters. And the third one will be the forecast. What is the weather forecast in the next, say, 30 minutes or an hour? So for example, I want to mimic the weather station in Toa Payoh having light rain, and it's also forecasted to continuous for light rain for the next 30 minutes. So as you can see, those with a keen eye, you notice that my mobile app, okay, which is running here on the left, will receive a push notification and displays a yellow warning. Okay, so let's go back to the simulator. Now, if it's raining in Toa Payoh, the rain must be coming from certain direction, and let's say it's coming from the northeast, which is probably Hougang. And let's say it's raining heavily over there. Okay, as you can see in my mobile app, because I'm situated in Toa Payoh and I'm not in Hougang, I do not receive any notifications. Now let's assume that the rain continues to pour. Okay, so the rain from light rain now, let's say it becomes moderate. Okay, you can see the changes, and from light rain it gets even heavier, and now we have thundery showers in Toa Payoh. Now, while the rain is coming from the northeast, okay, there may be also rain in Ang Mo Kio. So let's say it's moderate rain in Ang Mo Kio, and also probably light rain, some light rain in Bishan. So as you can see from the mobile app, okay, as the weather changes, as the real-time data gets inserted into our streaming application, okay, real-time notification can be sent out. Okay, so from a yellow warning to an orange warning, and then now to a red warning. Okay. Now, however, just as good things must all come to an end, all rain must also come to an end. So eventually, there will be fair weather and there will be no rain in Toa Payoh. Now, what you have seen here may be a little simplistic, but what we cannot do is to extend this mobile app to have other features. One such features that we have thought of is what we call My Subscription. So here, I can actually subscribe to multiple locations and will also receive notifications in real time from that locations depending on the weather situation. So as you can see here, we have earlier simulated moderate rain in Ang Mo Kio, light rain in Bishan, and even heavy rain in Hougang. Now that you have seen the demo, okay, let me show you how we have implemented it. First is our matrix, warning matrix. So by changing the rainfall and also changing the forecast, we are able to provide different types of warning levels. So different rainfall level and different forecast level will give different warning levels. So in our example earlier, you can see that I have selected heavy rainfall and also the forecast of heavy thunderstorm, and it will provide give me a red warning. So with this in mind, okay, let us explore further how we can achieve this using the power of stream processing. The backbone of our implementation is the event bus. This is where the real-time event stream processing happens. Now, in our simulated example, we have implemented three types of data. So the first is the subscriber location data. So this is basically the location of the subscriber, which is the mobile devices. In our earlier example, it has been in Toa Payoh, and I can also subscribe to different locations such as Bishan and Ang Mo Kio. Second is the rainfall data. So this is the current rainfall. Okay? The current rainfall data is constantly being streamed into the event bus. And third is the weather forecast data. So as the weather keeps changing, okay, the weather forecast will keep changing too. So we can always stream this in real time. So once the data is streamed into the event bus, we can then perform stream processing. We call this stream processing. Okay, the output of this can then be consumed by a alert service, in this case a flood warning service, which then in turn send out push notifications to the different mobile applications out there. So let's explore this a little further. So first we will explore the data. How are the data being consumed and how it looks like. Okay. So we will go through each of them individually. The first will be the subscriber location. So subscriber location is being streamed into the event bus. So what exactly do we mean by streaming and into the event bus? So first, think of it as a time-based stream of data, okay? And subscriber location is continuously being sent into the event bus. So for example, I'm subscriber 1 and I'm in Toa Payoh. So when I turn on my mobile app, okay, this particular data is being sent into the server. Now, as I'm walking around in Toa Payoh, that same information can also be sent into the event bus. Now, while this is ongoing, another subscriber in Bukit Batok will have probably turn on his mobile phone and it will send data. Similarly, then if I were to from Toa Payoh move to Bishan, and then immediately my mobile app will send a different data to the stream, and so on. You get the idea. The second data source that we want to talk about is rainfall. So for this, okay, we have streamed rainfall data from all the weather stations across Singapore. So typically, weather stations only send raw data. So for example, station 1, okay, the current rainfall is 15 mm. Station 3, the current rainfall is 20 mm. Station 2, the current rainfall is 25 mm. Now, having station code may not be sufficient for our example. Okay? We need to map this into a more meaningful location. Okay? We need to be able to map, say, station 1 is Toa Payoh or Bishan. So for this, okay, what we did was to ingest a simple code table into our event bus. Okay, so we have set up a weather station table with a UI that we can go ahead and configure the station code and the location. Okay, with this, we then perform stream processing, okay, by continuously joining these two data sets to provide, or to end result of it is to come up with a rainfall with location stream. Okay. So in this case, you can see that what we have done is that we have continuously joined the two sets of data, and it produces a new data set which basically has Ang Mo Kio 15 mm, Toa Payoh 20 mm, Bishan 25 mm. Okay, the last data source that we want to talk about is the weather forecast. Okay, so similarly, we have streamed weather forecast data from all the weather stations across Singapore. Okay, again, these data are in raw. So for example, the weather stations will send us data Ang Mo Kio CL, Bishan WD, Toa Payoh TH. And again, we need to be able to map this into something that is more meaningful. So what we did is to ingest another table, what we call the weather code table, into the event bus. We then perform the same type of stream processing, which is the continuous join, and the end result will be another stream which has more meaningful data, which in this example here, Ang Mo Kio, Fairlight, Bishan, Fairlight, Toa Payoh, AV. Second, let's explore stream processing. By now, we have our three data streams, the subscriber location, the rainfall with location stream, and also the forecast. However, data without process is meaningless. We want to process and analyze the stream data such that meaningful data can be generated for downstream usages. So to do that, we have performed continuous join and continuous analysis. So what do we mean by continuous join and continuous analysis? Let me show you an example to illustrate this. So let's assume for a while that the streams, the data it's all brand new and there's no data. And the first data that actually being ingested into the stream or into the event bus, okay, is a subscriber location. So in this case, subscriber 1 in Toa Payoh. Now, since that there is no other data, okay, that needs to be processed, okay, there will not be any warning. Now, let's say the weather station starts to send in data. So we will have a weather station in Ang Mo Kio sending 15 mm of data. Okay, immediately the stream actually picks this data up and start to process. Okay, in this case, there is no warning yet. Now, while of course since it's the same weather station for Ang Mo Kio, okay, that weather station will also be sending the forecast data. And again, immediately and continuously, the stream is processing it. There will be no warning sent out to the subscriber. Now, let's assume that the weather station continuously sending data. So now the data from Bishan comes in, both for the forecast and the rainfall. Okay, now, what happens if subscriber 1 were to actually move to Bishan? Now, immediately when the stream receives this data that is sent from the mobile app, okay, the stream will be able to process, analyze it, and be able to set out the first warning to the subscriber 1, which is located in Bishan and with the orange level. So similarly, if we were to continue doing this, okay, for more and more data comes in, okay, you can see that continuously, okay, as and when the data comes in, the stream actually processes it, analyzes it, and then output data that is for downstream usage. Okay, the last part that we want to explore is the alert service. So the alert service is a simple service that consumes the pre-analyzed data, okay, and then just sends push notifications to the subscribers. So in this example, the subscriber 1 will receive a orange alert, and the subscriber 3 will receive a yellow alert. Now let's put them all together. First, we have our data sources that is streamed into our event bus. Second, we perform stream processing to analyze the data. And third, we have an alert service that consumes the analyzed data to send out notifications to the subscribers. So with this, I've actually come to the end of the demonstration. Hopefully this short demonstration, you're able to see the power of stream processing. Even though the data sources that we have used in this demo is a little more simplistic, you can actually take this concept and build on it and ingest additional data. Maybe, for example, you want to ingest the level of water in the canals as a flood indicator, you can. The infrastructure allows you to actually ingest more additional data in real time. So, is stream processing the way to go? We think that batch processing is still relevant for strategical reports where data is not real time. So if you want to have monthly reports, it is still very relevant to do it using batch processing. Whereas, okay, for more time-sensitive operations, okay, we strongly feel that stream processing is the better option. With that, we have come to the end of what we want to share. So with that, we will go ahead and take some time for questions. So let me pull out the question panel and It looks like we have a couple of questions here. There's one particular question on the demo. So let me start with that. This question is from Andy. And the question is, how different is this join from the usual SQL join? So good question. So functionally, okay, the stream processing join and the traditional SQL join, functionally, they achieve the same thing. Okay. However, conceptually, they are vastly different. Okay. For stream processing, the join is continuous. Okay. For SQL, traditional SQL join, how do I say, the SQL statement or the action is executed once per call. So in order for a traditional SQL join to be able to do continuous data, you will typically require a batch job, and you will most likely need to time it such a way that it runs this particular query on a periodic basis. However, in stream processing, okay, this operation or this action is continuous. What we meant by that is that as and when the data comes in, okay, the stream processor will actually perform that particular action, in this case, the join, right, or even further more complex actions like analysis and so on, in order to produce the new data that you want. Okay, so in time-sensitive use cases, okay, we will definitely prefer stream processing. Okay, and as opposed to a batch processing system where there will be a significant time lag. So hopefully this answers your question on how different it is stream processing join versus SQL join.
Okay, I think there are some more additional questions. Maybe let me just pick some of it. So, okay, there's one question that looks like IoT applications are the main use case of stream processing. So, are there any non-IoT use cases? Okay, stream processing can be applied to many other use cases. Then that if that can benefit from the real-time processing itself. Right. So we have picked those IoT examples in this webinar as we feel that can be easily understood by the general audience as compared to a more domain-specific use case. So some of the examples of non-IoT use cases are transactionals, fraud detections, where you things like correlate across several transactional events. So we do things like you detect anomalies, you do data filtering, aggregations, or transformations for like ETL use case, just to name a few. Right. So you have specific areas. If let's say you have any specific areas in your domain that you think can potentially benefit from real-time stream processing, so do reach out to us. Then we can further discuss on your domain-specific scenarios. Okay. Let's see if there's any other questions. Okay, so there's another one that so are there any prerequisites for stream processing? Do we need an event-driven microservice architecture? Okay, in our previous webinars, we have talked about how having an event-driven microservices architectures will not only enhance the scalability and resiliencies of your applications, but you also create streams of business events, which you can subsequently leverage or tap on for other use cases and capabilities. So for example, by applying stream processing on your business event streams, you can derive real-time insights or triggers immediate actions when a certain condition is met. So in fact, there are also many other possibilities. So it's only limited imaginations. So while having an event-driven microservices architectures may not be suitable, may not be the absolute starting point for stream processing, we recommend taking these steps to build up your business events to a certain critical mass for stream processing to thrive. Okay, so let's see, any other questions? Okay, there's these questions stream processing seems like a more resource intensive process than batch processing. Would there be a higher hardware cost involved? Okay, definitely it will actually need the additional components in order to do this stream processing itself. I mean, we are not really looking at any particular product, but if I can name a product, or we can basically look at things like Kafka and stuff that is actually doing basically exactly what your stream processing is doing, right? So yeah, so it's instead of the batch processing components, it means you're looking at the stream processors and stuff like that. Okay. Okay, looks like I think we have answered most of our questions.
Okay, it looks like we have answered all of your questions. Thank you for staying with us throughout the session. We hope that you have enjoyed yourself as much as we do today. And most importantly, do remember to heads up to our YouTube channel, subscribe to our channel and give us a big thumbs up, or scan the QR code that is near to that you can see in our screen. Follow us on LinkedIn for more bite-sized kind of content. Thank you very much. See you next time. Goodbye.